So let's now talk about the graph of our logarithmic functions. What does the graph of y equals log base a of x look like? So before we do that, let's think back to chapter 1.9 again when we studied the graphs of inverse functions. Remember that inverses interchange the roles of x and y. This meant the domain of f of x, the domain of f inverse was equal to the range of f, and the range of f inverse is equal to the domain of f. And because of that, the graphs of inverse functions are reflections of each other over the line y equals x. All right, so here we have some function f of x. There I have the line y equals x. If I were to take the graph of f of x and reflect it over the line y equals x, that would leave me with my graph of my inverse function. All right, there I have the graph of f inverse of x. Similarly, here's another function g of x. If I take that graph and I reflect it over the line y equals x, I get the graph of my inverse. Remember, the roles of x and y are interchanged, which causes a reflection in the line y equals x for the graphs of any inverse function. So let's now apply that to our logarithmic functions. As we've said, logarithmic functions are the inverse of exponential functions. So what does this mean for the graph of our logarithmic functions? Well, let's compare the two. Starting off with our exponential function. Again, this is from section 3.1. We had f of x equals a raised to the x power. Notice that our variable x is located inside of the exponent. Hence, we call this the exponential function with a base of a. As we said, the domain for every single exponential function is all real numbers. So, how does this relate to our logarithmic functions? Well, this is going to become the range of our logarithmic functions. Again, all the x values and all the y values are going to flip for inverse functions. Now, what was the range of our exponential function y equals a to the x? Well, it was 0 to infinity. Okay, think about that nice exponential growth curve. What does that mean for my logarithmic function? How is it related? That is going to become the domain of my logarithmic function. Every single basic exponential function, y equals a to the x, had an intercept. It had a y-intercept at 0, 1. Recall that if we plug in 0 for x, a raised to the 0 power is equal to 1. Well, again, because all of our x and y values are going to flip-flop as we move to our logarithmic function, the inverse function, instead of having a y-intercept at 0, 1, we are going to have an x-intercept at 1, 0. And our exponential functions had a horizontal asymptote at y equals 0. Again, think about reflecting that over the line y equals x. What's going to happen? We now have a vertical asymptote for our logarithmic functions at x equals 0. All right, so given some logarithmic function g of x is equal to log base a of x, where a is greater than 1, the domain is going to be 0 to infinity. Okay, the range is going to be negative infinity to positive infinity. And the range of any logarithmic function, doesn't matter how we shift it, reflect it, scale it, the range of any logarithmic function is always going to be all real numbers. All right, our x-intercept for our logarithmic function log base a of x is going to be at 1, 0, and we have a vertical asymptote at x equals 0. All right, so let's see if we can't imagine what this looks like. Because exponential functions and logarithmic functions are inverses of each other, their graphs are reflections over the line y equals x, just like any other inverse function. So here I have the function f of x is equal to 2 raised to the x power. Here is my exponential function with a base of 2. Notice that we have a y-intercept at 0, 1, and a horizontal asymptote at y equals 0. Well, the inverse of this exponential function is g of x is equal to log base 2 of x. This is a logarithmic function with a base of 2. Notice that the inverse of the exponential function with a base of 2 is the logarithmic function with a base of 2. So instead of having this y-intercept at 0, 1, we now have an x-intercept at 1, 0. Instead of having a horizontal asymptote at y equals 0, we now have a vertical asymptote at x equals 0. And if we draw in the line y equals x, we take the graph of 2 raised to the x power and we flip it over that line. That will give us the shape of our function g of x. There we have it. There's the shape of g of x is equal to log base 2 of x. All right. Similarly, here we have the function f of x is equal to 5 raised to the x power. This is the exponential function with the base of 5. Again, same y-intercept at 0, 1, same horizontal asymptote at y equals 0. The corresponding inverse of the exponential function with a base of 5 is the logarithmic function with a base of 5. G of x is equal to log base 5 of x. Well, how is this graph going to be related? Instead of having a y-intercept at 0, 1, we have an x-intercept at 1, 0. Instead of having our horizontal asymptote at y equals 0, we have a vertical asymptote at x equals 0. Okay? And if we reflect our graph over the line y equals x, we end up with our function g of x. There we have in red the curve g of x is equal to log base 5 of x. All right? Again, the logarithmic function with a base of 5 is the inverse of the exponential function with a base of 5. What about the natural logarithmic function? Natural. So you might recall our natural exponential function was y equals e to the x. The inverse of y equals e raised to the x power is the natural logarithmic function and is denoted by y equals ln of x. All right, it is important to note that ln of x is the exact same thing as log base e of x. Okay, these mean the exact same thing, ln of x and log base e of x. So here we have f of x is equal to e raised to the x power. Here is our natural exponential function. And again, same y-intercept, 0, 1, same horizontal asymptote, y equals 0. What's going to happen if we reflect this graph over the line y equals x? My y-intercept now becomes an x-intercept. My horizontal asymptote now becomes a vertical asymptote. And I now have the graph of g of x is equal to ln of x, log base e of x. ln of x is the inverse function of e to the x. All right, and a couple properties of our natural logarithms. Now, you actually already have these properties written down in your notes, right? We talked about these with our other bases of our logs. Log base a of 1 is equal to 0. Same thing applies with ln of 1. ln of 1 is equal to 0. Why? This is e raised to the 0 power is equal to 1. ln of e is equal to 1. This is saying e raised to the first power is equal to e. So we can simplify ln of e into 1. If ln of x equals ln of y, then x must equal y. Here I have two logarithmic quantities set equal to each other. If they are equal, the quantities inside of the logs must be equal. That was our one-to-one property. And ln of e to the x is equal to x, and e to the ln of x is equal to x. Those were our inverse properties as well. All right, so four properties of logarithms that you guys have already seen, now just being applied to our natural logarithm, y equals ln of x. All right, we have one more special log to talk about, and that is the common logarithmic function. The inverse of the exponential function y equals 10 to the x is called the common logarithmic function, and it is denoted y equals log of x. Notice that no base is written here. If no base is written, it is assumed that the base is 10. This is known as the common log. No subscript of the log means log base 10, right? Log of x and log base 10 of x are identical. All right, and so here we have the exponential function, y equals 10 raised to the x power. Again, we have the same y-intercept at 0, 1, the same horizontal asymptote at y equals 0. Well, to get the inverse, we need to reflect that graph over the line y equals x. That turns my y-intercept into an x-intercept, my horizontal asymptote into a vertical asymptote, and reflecting that graph over our line gives us g of x is equal to log of x. Okay, log of x is the inverse function of 10 raised to the x. And just like with all of our other logs, we have properties of common logarithms, the exact same four properties that you have seen before. Log of 1 is equal to 0. Log of 10 is equal to 1. If log of x is equal to log y, then x must be equal to y. That's our 1-to-1 property. Log of 10 raised to the x power is equal to x, and 10 raised to the log of x is equal to x as well. Those were our two inverse properties. All right, so now you have a good idea of what the shape of all of our logarithmic functions looks like. What do you think we're going to do next? Transform them. You got it.